The equation of the vertical line x is equal to a is a vertical asymptote of a function if the absolute value of f(x) goes to infinity as x approaches a from the right or as x approaches a from the left. So let me draw what a vertical asymptote looks like. So if here's our graph, let's say that this right here is the vertical line, x is equal to a. What it's saying is that as our function approaches a, if our values go to, our y values go to infinity, then it is a vertical asymptote. So I had something that looked like this. They don't have to be on opposite sides like this. We can have both of them going to positive infinity, both of them going to negative infinity. And actually, let me explain this notation real quick. Actually, maybe most people probably haven't seen this. As x goes to a with a plus sign, that means we're approaching a from the right. And if there's a minus sign, as x goes to a with a little minus sign, that means as x approaches a from the left side. So that's all that means. And here it says that a function is a vertical asymptote if the absolute value of x, or the function, or the absolute value of the function of x approaches infinity. I don't know why I just said x, but the function of x approaches infinity, then it is an asymptote. Here we can see that it approaches infinity, and here it approaches infinity. Here it is approaching minus infinity. So as our x values get closer and closer to a, our y values are going to infinity. And in this case, it's negative infinity, but since this is an absolute value, it doesn't matter. And that's what it's saying. Here we can see that as we get closer to a, y goes to infinity. So now that we know what the definition of a vertical asymptote is and what they look like, let's do an example and talk about what's causing that vertical asymptote. Why are the numbers behaving that way? So let me use the example f of x is equal to 1 over x minus 1. So we need to figure out where our function may possibly be undefined. And actually, let me explain one more thing. Vertical asymptotes occur where a function is undefined. It doesn't, just because a function is undefined somewhere does not necessarily mean it will be a vertical asymptote. We could have a hole there. A function is undefined there, but it's not a vertical asymptote. But it has the potential. Anywhere where there is an undefined in our rational functions, there's a potential for it to be a vertical asymptote. And what distinguishes a vertical asymptote from a hole is as we approach a, it goes to infinity. When we have a hole, so let's say this is a line, a hole, it's not going to approach infinity. It's just going to carry on. Then all of a sudden we're going to have just an undefined value, and then it's just going to continue carrying on. It does not go to infinity. So that's what distinguishes a hole from a vertical asymptote. But let's identify the numbers that will cause us to be undefined. The only one is x cannot equal 1. If we put in 1, we'll get 1 over 0, and it will be undefined. So here we can just put that a is equal to 1. Now to check and see if this is a vertical asymptote, we need to approach it. We need to approach 1 from the right, and we need to approach 1 from the left. And what I'm going to do is I'm going to make a table and try to illustrate what is happening with that. And first, let's approach 1 from the right. Now what I'm going to do is I'm going to approach 1 from the right, and I'm going to find out what the function value is at various distances from A. So let's pick a few distances. Let's say I want to find the function value when I'm 10 units away from A, when I'm 5 units away, when I'm 1 unit away, when I'm 0.1 units away, 0.01 units away, and 0.001 units away. So let's find all of these distances. What we're going to do is we're going to see what happens to y as we get closer and closer to x. I'm going to start 10 units away, then we're going to get 5, then 1, then 0.1, then 0.01, then 0.001, and we'll see what happens. So in order to be 10 units away from A, I'm going to need to put in 11, at least from the right. So if I put in 11, I'm going to get 1 over 10, which is 0.1. And I'm going to do these in decimals. If you would like to convert these to fractions, you can. There's no rule against it or anything like that. It's just that, in my experience, people in math don't generally deal, most people in real life don't generally deal with fractions. When you go to the grocery store or something like that, or someone asks you to describe how big something is, or how much of something there is, they don't generally give you some fraction. They don't give you like 99 out of 100. They'll say something else. Or they don't say 1/10, they'll say 0.1 or 0.001 or 0.385. Those are the numbers people are used to hearing to, so that's what I'm going to do this in. But it's fine if you'd like to do it in fractions. So 10 units away, so somewhere out here, the function value, the y, is 0.1. Now let's see what happens when we are 5 units away. So in order to be 5 units away from A, we need to put in 6. 6 minus 1 is 1/5, or 0.2. So I started at 10, then I've gone to 5. Started 10 units away, now I've gone to 5 units away. And I've increased from 0.1 to 0.2 over 5 units. Now, for 1 unit away, that's going to be 2. So if I put in 2, I'm going to get 1 over 1, which is 1. So we can see here that we're starting to increase a little bit faster. From 11 to 6, we increased from 0.1 to 0.2, so we doubled. But then from 6 to 2, which is from 5 units to 1 unit. So originally we were 10 units away, we went to 5 units away. And we went from 0.1, a function value of 0.1 to 0.2, so we doubled over 5 units. Now I've gone from 5 units to 1 unit, so a difference of 4 units. And I've more than doubled now. I've gone from 0.2 to 1. That's a difference of 0.8. So we've doubled a few times. We've doubled. More than doubled. So we can see that we're increasing a little bit faster per unit. So going over 1 this way is not equal to going over 1 a little bit closer, or 1 a little bit closer. So let's do 0.1 units away. To be 0.1 units away from 1, it's 1.1. 1 minus 1.1 will give me 1 over 0.1. And if we want to do this in fractions, 1 over 1/10. And we know about fractions. A fraction divided by fraction is the same as multiplying by the reciprocal. So this is 1 over 1 times 10 over 1, which is 10. So if I put in 0.1, 1.1, I get 10. So the rate we're increasing has increased even more now. We've gone from 1 to 0.1, and 1 was a 1, But 0.1 is a 10, so we've increased even more. We haven't even increased by 1. And we've increased by 10. Or 9, if we're going to do a difference between 1. So let's put in this now. So this is 1.01. And this is going to give me 100. And if I put in 0.001, that's going to be 0.001. This is going to give me 1,000. So we can see as we get closer and closer to A. So let's graph this. So we started out at 10 units away, and we were at 0.1, which is, who knows, it's like right down here. Then we got to 5, and we were at 0.2. And then we got to 1, and then, 1 unit away. Not the actual x is equal to 1. X is equal to 2, which is 1 unit away. Now that we're 1 unit away, we've increased to 1. Then once we got to 0.1, then we already increased to 10. And then we continue increasing just exponentially. Where 0.01 is already 100. If we were to put in 1 millionth, it'd be a million. So we can see that the closer and closer and closer we get, it's just going to continue to get more ridiculously large as we approach it from the right. So we can already say that there is a vertical asymptote. So this is going to infinity. So let's write this. So these values are going to go to infinity as we get smaller. And now let's approach it from the left side and see what happens. We can do this right here. So x, y, and we want to do the same thing. 10 units away, 5 units away, 1 unit away, 0.1 units away, 0.01 units away, and 0.001 units away. So in order to be 10 units away from 1 in a negative direction, I need to subtract 10 from 1. That's going to give me minus 9. Here's our function again. 1 over x minus... Oh, so let me write it over here again. 1 over x minus 1. Minus 9 minus 1 is minus 10. And 1 over minus 10, that's minus 0.1. Now to be 5 units away, I need to subtract 5. And that's going to give me minus 4. Minus 4 minus 1. It's 1 over minus 5. Minus 0.2. To be 1 unit away, I subtract. I'm going to be at 0. So I subtract. So 0 subtract 1. 1 divided by minus 1, it's minus 1. We're going to get the same thing, but just going in a minus direction. To be 0.1 units away, I have to subtract 0.1 from A. That's going to give me 0.9. So if I put in 0.9, I'm going to get minus 0.1. That's going to be minus 10. If I want to be 0.01 away, I have to put in 0.99. It's going to be minus 100. To be 0.001 away, I have to put in 0.999. That's going to be minus 1,000. So we can see that this is also going to infinity. More specifically, negative infinity. As these get closer to A. So that will look like that. So as our values... So we've discovered that as our values get closer to A, it goes to infinity. It happens that when we approach it from the left, it goes to minus infinity, and when we approach it to the right, it goes to positive infinity. So I think that should answer most questions on the asymptotes. I guess there is one, which is what happens at, if they're getting so close to A, what is happening at A? That's to say that we don't know. It's undefined. I don't really know any way to explain it. Actually, I can think of only one person who can possibly explain what is going on. I'll put a link to it actually because it's beyond my qualifications to explain. So if you really want to know what's happening at A for this function, click on that link. But now that we know how it's working, let's talk about real briefly why this is happening. Let's just talk about fractions in general. Say I have a fraction 1 over x. If I put in large values for x, then the result is going to be a small number. So if I have large values in my denominator, then we're going to get small answers. If I put 1 divided by 100, that's small. If I get larger, 1 divided by 1,000, that's even smaller. If I put in 1 divided by 1,000,000, that's going to be even smaller. So as I put larger and larger numbers in here, then it's going to be a smaller total value. But let's see what happens when we put in small values for x. If I put in a small value, like 1/10, like how I demonstrated earlier, if I put in 1 over 1/10, then this is going to give me, this is the same as 1 over 1 times 10 over 1, which is 10. And if I put in 100th, that's 1 over 100. This is 1 over 1 times 100 over 1. Then the values are going to get larger. Then the values are going to get larger. So this is what is causing the asymptotes. Or that's what's, it's not really what's causing, that's what's causing the numbers to go to infinity. One thing I forgot to mention is how to find vertical asymptotes, and obviously that's a little bit important. So let me go over that very quickly. When we have a rational function n of x divided by d of x, which is the numerator, which is some function in the numerator and some function in the denominator. When we simplify it and we get to a point where there are no common factors between these, so no factors, or common factors, and it's as reduced as it can be, then we look into our denominator for values of a that give 0 or an undefined. And those are going to be our vertical asymptotes. So to use our previous example, we had put 1 over x minus 1. And we can see that there are no common factors between the numerator and denominator. And then we look to see, so no common factors. So now we just look in our denominator and see what values of a give 0. And a is equal to 1 gives an undefined answer, or a 0 in the denominator. And we can have multiple asymptotes. So let's take something like, let me give a couple of quick examples just to give you a general idea. So f of x is equal to 1 over x minus 2 times x plus 2. So this is a quadratic equation down here, and we can see that there are, between the numerator and denominators, there are no common factors. So this is in lowest terms, so what a numbers are going to give us are going to give us 0 in the denominator? Well, 2 and minus 2. So we would have vertical asymptotes at a is equal to 2 and a is equal to minus 2. So horizontal lines 2 and minus 2 where they cannot cross. Let me give you one more example where we have to divide something out. So let's say if we had this, but we had an x plus 2 in the top. In this situation, we do have a common factor, x plus 2. We can cancel these out and write this is equal to 1 over x minus 2. X cannot be equal to negative 2. And we have no more common factors between the top and the bottom, and we have an a equal to 2 that will give us a 0 or an undefined answer in the denominator. So this has one vertical asymptote at x is equal to 2. And what the other thing is, as we learned previously, this is a hole. This is not a vertical asymptote. So our vertical asymptote at x is equal to minus 2 in the previous example is a hole in this example. It doesn't go to infinity. It's still undefined. This is still undefined at x is equal to negative 2, but it doesn't go to infinity. So that's how we find vertical asymptotes. And we're going to learn next about horizontal asymptotes and oblique asymptotes, which are asymptotes in diagonal lines.